Okay. So today I'll be teaching a crash course on using Gdb and Valgrind to debug in C. First of all, what can I use Gdb for? So Gdb is really useful if you want to figure out why your program is crashing, or why it gives incorrect output, or you want to visualize how an algorithm runs by stepping through it one line at a time without having to add a bunch of printfs and recompile. Typically, I've always done a lot of printf adding, and it's a really huge pain, especially when when printf might not work on embedded systems. So being able to just debug it like this is really a lifesaver. So just so I can get an idea of how much experience people have, who here has used Gdb before? Okay. And for the rest of you, I assume that this will be your first exposure to it, which is fine. I'll start from the very basics, and I'll try to go over the most common use cases and cover some stuff that even if you have used Gdb, it will still be helpful and maybe new to you. So the whole time, what we're going to do is we'll use Gdb to debug a buggy program that I wrote for this. So in order for you all to get a copy of the code, you'll want to run git clone followed by that URL. So we'll all do that right now, and I'll just give you guys a little bit to get that working. All right, have all of you checked out the code, or cloned the code? I'll take it as a yes. Next, you'll run Git Checkout Minimal. This will start us out on the branch that has a minimal example that will get us started with Gdb. So now what I'm going to do is I'm going to use, I'll zoom so you can see that. I'm going to use GCC to compile the code. So first let me make sure I'm on the minimal branch. And now I'm going to type gcc leapyear.c-o leapyear, and that will compile the code. So the purpose of this program is a really simple and really conceited example that's supposed to tell us whether a year that is input to the program is a leap year or is not a leap year. People who have taken W10 before will probably remember this example. So right now, let's give it a try. If you look in the file testyears.txt, you'll see that here there's a very small sample of years to test this on. And if we look in the file testyearsoutput.txt, that's the output that we expect from this program. It will give us a 0 if it's not a leap year and a 1 if it is. So let's run it right now. The syntax is leap year and then the year. So for example, I'm going to try 1715. And it correctly says 1715 is not a leap year. So now I'm the leap years down here. Let's try 1800. 1800 is also not a leap year. The pattern for a year being a leap year is if the year is divisible by 4, but is not divisible by 100 unless it's divisible by 400, then it's a leap year. And I'll have that on the next slide. But so far the output seems to be correct. 1900, that's correct. And when we get to 2000 though, it's saying that 2000 is not a leap year. But here we can clearly see that 2000 is supposed to be a leap year, because although it's divisible by 100, it's also divisible by 400. So what we're going to do now is we're going to try to use Gdb to figure out why this program is saying that 2000 is not a leap year. And if we want to check the remaining cases, we can see that for the remaining 2, it does give us the correct output. So what we're going to do next is we're going to compile for debugging. And the way we do this is we add the -g flag. What the -g flag does is it tells GCC, when you build this program, include information about which source lines are connected with or associated with which object code lines. So in a simple sense, it allows us to tell what is going on, whereas otherwise we just have the raw machine code to guide us. So right now we're going to repeat that same GCC command to compile, except this time I'm going to add the -g flag. leapyear.c. So now, just as before, we have an executable called leapyear, except this time it has debugging symbols in it. And you can do the same thing anytime you're using a makefile as well. If you have a makefile that's in charge of telling the computer how to build your program, you can add the -g flag to the environmental variable called cflags. And we'll see later on how to do that. But that will have exactly the same effect. So now, in order to run this program with Gdb, what we'll do is we'll type gdb leapyear. And as you can see here, it says reading symbols from leapyear, done. When you see that, you know that the program has symbols. So you know that the -g flag was used and you're good to go. In order to run the program in Gdb, you can type just the letter R, which is short for run, or you can type out the U and the N as well if you're feeling adventurous. And that just gave me the usage, as you can see. When you run something in Gdb, you add all the arguments after the statement run, in the same way that you would add them after the name of the program if you were running the program from the terminal. So in this case, because the program takes a year, we'll type R2000. And as you can see, it's giving us the same output that we previously got, except this time it's running inside of Gdb. So that will give us more of an idea of what's going on. So right now, this isn't really helping at all. We run the program inside of Gdb and it runs from the beginning to the end and doesn't give us any information. What would really help is if we can tell the program to stop partway through and then take a look at what's going on. And so what we'll use in order to do this is what's called breakpoints. And a breakpoint is simply a point in the code. It could be a line number or a certain function that when the code is run to that location, execution will be paused. And then that will give us some time to look around and see what's going on at that point in the program. So you can break, there's many different ways you can specify a location to break at. You can specify a line number, you can specify a file and a line number, you can specify a function, in which case it will break as soon as that function is called before it runs anything inside of the function. There's other combinations as well, which I won't go into because these are the most common, but you can find all of them in the Gdb documentation. And if you type help breakpoints inside of Gdb, it will also give you commands relating to breakpoints. So after you hit a breakpoint, you can type C, short for continue, to keep on running. You can also list all the breakpoints you have with IB or info break, and you can delete one or more breakpoints by using the D, short for delete command, followed by the breakpoint number. So right now, let's see if we can set a breakpoint in our code that will make it more obvious what's going on. So I'm going to go in leapyear.c so we can see what the code actually looks like. And okay, you guys can see that there. So this program is really simple, as you can see. All we have down here is a main function which takes an argument from the user. And then it passes that number to the function isLeapYear, which then calculates whether or not it's a leap year. And it should be pretty obvious. Where do you guys think the error is in, like, which function here? We've got three functions: main, usage, and isLeapYear.
isLeapYear.
Wow, Peter, you're so smart. Peter is correct. The bug is most likely in isLeapYear. So what we'll do is we'll set a breakpoint at isLeapYear, and we'll see if we can step through that function and see exactly what's going on there. So Everin, right now in Gdb, you'll want to type b isLeapYear. And Gdb has tab completion as well, so you don't have to type out the whole thing. And as you can see, it's set a breakpoint number 1, at this memory address. And it tells you what file and what line it's set at. So now what we can do is we can run the program just as we would from the beginning, run 2000. is the argument. As you can see here, the program started and it reached breakpoint 1, and then it stopped right there. And right here, we have a display of what the current line number is that we're on and what the line that's about to be run is. So as you see right now, we're stopped at line 11 and we're about to run if year modulo 4 to check if year is divisible by 4. So breakpoints wouldn't be that useful if we could only stay stuck at a breakpoint. It would be a huge pain if we had to set a breakpoint every time we wanted to stop or step forward. So that's why Gdb has some useful commands that help us move around inside of the program and see what's happening one step at a time. The first one is L, which simply lists out the source code that's where you are right now. So right now, if I type L, you can see that it shows us our surroundings, and we're right there on line 11. If you keep on typing L, it will actually move down through the program and display later lines, which can be kind of confusing if you're new to Gdb. So keep that in mind. We can also go to the next line by typing N, which is short for next. And it's important to note that when we type N, it will run everything in the line that's there. So if we call a program in that line, it will run the whole program and then go to the next line. So if we want to get more information about what's going on inside of a program that we call in that line, we'll use the step command. And what step does, abbreviated by S, it runs one instruction. So if you're taking CS24 or have taken it, you'll know that instruction is a lot of times much smaller than a line of code in your program. In order to finish executing the current function that we're in case we accidentally stepped into a function and we want to get out, we can type fin, short for finish. If we want to run until a certain line, then we type U, short for until, and then the line number. That's really helpful if we're, for example, stuck in a for loop and we want to get outside of that loop, then we'll just type U and then the line number. Are there any questions about moving around so far? Okay. So right now what we'll do is, let's start moving through the program. Let's just start by going to the next line. So type N, and you can see that what happens, can everyone tell me, does it step to the very next line when we type N? Nikhil, you're nodding your head. Did it step to the next line for you? Are you looking at the line number on the left? Because it didn't for me.
No.
No, it did not. Yeah. Kind of a trick question because you think N only runs one line, but what happens is we had a conditional there, and that conditional evaluated to false. So when we typed N, it skipped over everything that was in those braces. Can everyone see that? So we skipped from line 11 to line 14. And I've got the code down here so you can see it was just if year modulo 4 that we just skipped over. So does that make sense with the value of year that we have? Well, let's see if it makes sense. Sure, we ran the program with 2000, but can we really be sure that year is still 2000? It's probably good if we make sure. So we could have just looked at when we reached the breakpoint. It tells you what the value of year is there. But in general, if you want to look at other local variables, that's not always the case. So that's where the print command is handy. If you type P, short for print, followed by an expression, Gdb will tell you what that expression is. So right now, let's print what's in year. Just type P year. And as you can see, it's 2000. So what's handy about print is that it can print expressions, not just single variables. So we could, for example, see what year modulo 4 is. P year modulo 4. And we see that's 0. You can have arbitrarily complex expressions with multiple local and global variables, and you can dereference pointers. Pretty much everything that you can do in C, in a C expression, you can do in Gdb when you're at a breakpoint. Or just pause in general. Another handy thing that you can do which you should also be careful about doing, is using the set command. You can set the value of variables when you're paused in Gdb. And this is maybe useful if you want to see how part of the program responds to a certain value, a quick way to run a test or something. As you can see here, you can also set one variable equal to the value in another, or even dereference a pointer. And finally, you can call a function. And calling is really useful if you, for example, want to call a helper function to see the length of a string, or if you want to see how your function that you've written is behaving under the current state of the program. So, with that being said, I think it's time that we step through the rest of this is leap year function and see what's actually going on here. So, year is 2000. What do we expect year modulo 100 to be? Yeah, obviously, it's 0. So we expect it to skip over that statement because it will give us 0, so it will evaluate to false. So we type next. What do we expect? Is year divisible by 400? Yes. So we'd expect that this statement, if you ignore the obvious bug in it, would give us 0. Or sorry, would give us, yeah. So year modulo 400 is 0. But here's the thing. If we go next here, we can see that we have skipped right over this if statement right here. Does anyone, this would be pretty obvious if you're familiar with C. Does anyone know what the bug is right here? Why did we not return true on line 18, even though year is 2000? Yeah, the operator precedence is wrong. The not there is being applied to year before the modulo is. To make it clear what's going on, I'll just show it in Gdb right here. We have year is 2000, and year modulo 400 is, oh yeah, I forgot the P. Year modulo 400 is 0. However, not year modulo 400 is also 0, and that's because the not is associating with the year first and making that 0. And then when we take that modulo 400, it's still giving us 0. So obviously the correct solution here is to put some parentheses around the year modulo 400, and then that will give us the one that we expect. Is that clear to everyone? Okay, so let's fix that right now in our code. I'm just going to go down here and insert those parentheses. Okay. Now what we can do in Gdb, you don't, actually never mind. This will come later. First, let's just recompile by using the same DCC command that we used earlier. And now we can run leap year with 2000, and as expected, the return value is 1, indicating that that is a leap year. We can also go back to the previous test cases, and they all match up. And granted, this is a really shitty set of test cases here. Ideally, if we had any chance, we'd run it with a lot more than like 5 values. This is for the sake of running here. Okay, so that was a pretty simple example. Now that we know how to set breakpoints, move around and look at things, it's time to get into some more advanced debugging. And so one of the problems that a lot of you have undoubtedly run into is seg faults. So seg faults is a memory segmentation fault, which happens when you illegally access memory that you're not supposed to. So right now what we're going to do is work with a program that's similar to the first few CS24 assignments almost. Once again, it's really a conceited example where we want to read a list of years and months from a file, and then we're going to print the number of days in each month. In order to access this code, you're going to type Git Checkout Master. I can spell it. Oh, you'll want to discard your changes first, or else it won't let you. So do Git Checkout -- dot. Everyone got that? Git Checkout -- 2 dashes right next to each other, space dot. Okay. And now you can Git Checkout master. I can spell, I swear. Okay. So now we're going to run this example. So first, I provide a make file. So type make, and that will make the program. And now what we're going to do is we're going to run it on some test states, which are in the file teststates.txt. I'm just going to pull that. So we can see it's in the same format as the float sum example from CS24, where we have the number of dates at the top and then followed by the data itself. We also have some example test output here in output.txt. That's what we'd expect if the program output were correct. So I'm going to keep the example output down there, and now I'm going to run the date count program here. So I'm going to run date count, and then you're going to use the lesson sign to pipe the contents of the test states file into the program. And as you can see, it gives us a seg fault. So what we're going to do now is we're going to add the -c flag so that we can run Gdb on this, and then we're going to make it again so that we can debug it. So right now, edit the make file. And as you can see, this is a really simple make file. A lot of times you'll encounter more complex ones, but the important thing is just to find the C flags environmental variable, or whatever is used to pass the flags to the chain. And you're going to add the -c flag to the end of the C flags. Everyone got that? Okay. Now let's make clean and make again. And now we've made with the new rules. Okay. So once again, we're going to run the program Gdb by typing Gdb date count. And now we're going to type run. And once again, remember that when you use run, you add on the arguments in exactly the same way as you would in the shell. So in this case, we're going to pipe the file into run in exactly the same way that we would if we were just at the shell normal. So date, I forgot what the file name is. Teststates.txt. That's it. Okay, and right now we have some more information because we can see where exactly the segmentation fault happened. Can anyone tell me why exactly this segmentation fault is happening here? Why is it happening on that line? So we're dealing with an array here, right? So there's only really one possible thing we can be doing with an array that would cause a segmentation fault. Do you guys know what it is?
Is the month 0? I'm just trying to
That's a good guess. And you are right, it's an out of bounds problem. What's happening in this case, we can actually see more clearly right here that it shows us what month is. Can you guys see that value? So you had the right idea, but it's on the opposite end. Instead of being -1, it's out of bounds on the other end of the spectrum. It's absolutely huge. It's ridiculous. So what we're trying to do is we're trying to access the however big that value is. It's like 540 millionth value of month, and obviously our month table only has 12 elements in it. So we're trying to access something that's obviously not in our array, and that's what's causing the illegal memory access. So the real question, I guess, is why does month have such a bad value here? And so where we are right now, we don't really have much information about that, because let me open up the program. Right now, we're inside of the get end days function right here. And so we were already passing the bad value of month. So obviously the problem that we're dealing with right now arose outside of this function. So this is where the being able to see the stack is really helpful. Because when your program crashes, a lot of times it won't even be in your own code. It will be like 12 or 13 calls deep into some library code that doesn't even have debugging symbols in it. And so what you're going to want to do then is figure out what caused that bad value to be propagated in there and caused the crash. So who here is familiar with the stack and what the stack is? I'm assuming the CS24 people. Don't be shy, raise your hands. If you're in CS24, you know what the stack is. Yeah, so pretty much everyone. Well, the stack will basically show all the function calls that have transpired to get us where we are. So if we type bt, sort for backtrace, then we can see the current state of the stack, and we can see that we're in get end days, obviously, and that we've been called by main. So what we're going to want to do is we're going to want to go up into main so that we can see what was the process by which this erroneous data was given to get end days. So if we type up, then it will take us up a level, and now we're in main. So let's take a look at some of the data that we're working with here. Let's take a look at what da.dates is. Da.dates, if we look at the code down here, is a pointer. This is the struct that we have. So it has a pointer to some chunk of memory that we're using to store dates. And it has, this struct also has a count that tells us how many elements there are in that array. So a lot of times it's really useful to see the whole array at once. And so we could do element-wise access like pa.dates 0 or 1. But another handy thing to note is you can just type p followed by the array name and it will print out the whole array. However, if it's dynamically allocated or if it's a pointer rather than being an explicit statically allocated array, then you'll need to specify how many elements to print out. So in this case, you can use the shorthand p and then the star, the pointer, and then the @ sign followed by the number of elements. So in this case, we can type p star da.dates at da.count. As you see, the number of elements to print can also be a runtime expression. It doesn't have to be some immediate value. So here we can see that the data starts out fine, and then after the first, where is that? The first 3 elements are fine, and then after that, the data is just really whack. So what we want to do is we want to figure out exactly how that data got corrupted. Does anyone have any guesses? There's a few functions in here that could be to blame. We have the load dates function that loads the dates from a file. We have the isLeapYear function, that's probably not a problem, and get end days. It seems like it's most likely the load dates function. And just out of curiosity, has anyone already identified what the bug is? Don't say it, but just raise your hand if you've already figured it out. Okay, this one's tougher, so I guess we'll actually have to go through the full process. So what we're going to do now is we're going to, first of all, check that the load function is working correctly. Because a lot of times, it could be possible that the way that you load data is flawed and that the values you're getting from the text file are just completely wrong. So where do you guys think we should set a breakpoint? There's multiple correct answers, just give you some ideas. If we want to make sure that the dates that we're loading from the file are correct. We can break anywhere we want. It's just that some locations are going to be more convenient. So, any suggestions? Yo, Mike, you got any ideas? 70? Yeah, 70 is fine. We can break it 70. So let's type v70. That was a fine choice. Really, any place after we load the dates from the file is fine. So we'll just see how it looks from here. We'll v70 and then we'll run from the beginning. So we'll type run and then type in I forget what the file name is. Yeah, it's, what is that? I can't see the file name. So that's, is it test dates.txt? Yeah. Okay, here we are at line number 70. So let's take another look at dates here. So once again, we can use the same shorthand, although now, if you take a look at the function where we are, we don't have the DA structure, we're just dealing with the raw array called dates. So we'll do dates count. Okay, so the location you chose is actually a little bit earlier than ideal, because we chose a location before we load the dates from the file. But that's fine, because what we can do is we can run to line 79 or something. So line 79, as you can see, is like at the very bottom. So we can just do U79. Yeah. So type U79, which again is short for until 79, and that will get us to the end, so we can actually see if the dates are correct. And then once again, we'll do pData_count. And as you can see, everything looks fine here. So something's changing in between here and when we actually call the get end dates function. So let's type n a few times, and we can see that now we're back in main at line 86, right when we go into that for loop there. So if we type C though to continue, then you can see that we have exactly the same segfault as before. So what would be really helpful is if we can figure out where the dates get changed, because obviously we load the dates properly and all of the data in there seems to be right. But then later on, something is somehow changing that value. So that's where watch points become really useful. A watch point is like a breakpoint in that it pauses the execution of your program. The difference is that a watch point pauses the program not when it reaches a specific point, but when the value of an expression changes. For example, let's say that you want to figure out every time someone changed a value called x. Then you type watch x, and you'd run the program and it would automatically stop as soon as something made a change to that variable. What's nifty about watch is that just like some of the other expressions like print we've seen, it can watch entire expressions, not just single variables. So for example, if we wanted to watch the value of the expression x over y plus a times b, we could just type watch followed by the expression, and everything would work as we anticipate. I'm not sure how often you'll actually use that, but it's a good feature to know about. The same commands about like info and delete, disable, and enable work with watch points as well as breakpoints, where if you want to temporarily stop using a watch point, you can type disable, and then you can re-enable it. If you want to delete it, you type delete or D. And just like breakpoints, watch points are numbered, and you follow these commands by the number that corresponds to the watch point you want to modify. So what we'd like to do right now, what do you guys think would be a good variable to watch? Like what's changing that we don't want it to change?
Dates.
Yeah, exactly. And is everything in dates changing? Or is it just some parts of the dates array?
Not sure.
Okay, if we scroll back in here, we'll see that, can everyone see the lines I'm commenting right, or highlighting right here? It looks like it's good except for the last three elements. So you're right that dates is being changed erroneously. It's not all of it, it's just the last three elements. So we'll probably want to watch those specific elements because the other ones might not change. So one thing I should mention about watch points is in C, as you know, variables only persist within their scope. So if you declare a local variable inside of a function, then you can only access that variable inside of the function. And unfortunately, or perhaps fortunately, watch points work the same way. When you watch a variable, you can only keep that watch point for as long as you're inside of the function or the scope for which it's defined. So for that reason, we'll want to set a breakpoint when we're inside of a scope where we can set the watch point properly. Does that make sense? So we'll want to get inside of that function. In this case, it's main, but we'll want to get inside of main at the right point, and then we're going to break there, pause there, and set a watch point on the variable. So let's delete the breakpoints by typing D, and confirm that you want to delete all breakpoints. And now what we're going to do is let's figure out a good place to put our breakpoint where we can set a watch on the dates and figure out where they change. So we saw that dates were good up to line 86. Does everyone remember that? We were inside the load dates function and we saw that everything loaded apparently correctly, and we got outside that function and we actually didn't look at it again, but I'll assure you that everything is still okay at this point. So 86, does everyone agree, would be a good place to break? So let's put a breakpoint on line 86. So B space 86. In the case that you're working with multiple files, you can't just put a line number. You should also put the file name before that and a colon. Otherwise, it will just put the breakpoint in the current file that you're in, which you may or may not want. So it's always good to specify. Now let's run it from the beginning by typing run testdates.txt. Okay, so right here, once again, we can print out the dates just to assure everyone that they're all right. They haven't been modified yet. And now let's watch a specific date that we've seen to change as a result of the bug. So I'm going to type watch da.dates, and then let's see, 0, 1, 2, 3. As you can see, it set a hardware watch point. What that means is that this watch point is actually supported in the hardware of the machine. This type of watch point is much faster. Otherwise, the machine has to stop after every single instruction and check if the value has changed. But if you've got a hardware watch point, it's really nice because there's actually hardware inside of your processor that will detect when that certain register has changed in that scope. So what we're going to do now is we're going to continue by typing C. Does everyone see what happened? We've hit the watch point. Which function are we in? Does that help? So we've crashed inside of a function that's not actually something that we've written. And this is actually a malloc function. And so that's kind of a pain, but it does give us some clues to know what's going on here. Are there any points in the code where we mess with things that could affect how malloc works? You guys can look through the code on your editors if you want, if that's helpful. Or even in what parts of the code did we deal with memory allocation? We have, did I hear someone say something? I guess not. We have one called malloc, which is on line 63. Can you see it there? And the fact that we crashed inside of malloc previously should tell us that something's, or we didn't crash inside of malloc, that's bad phrasing. What happened is that malloc overwrote the value that we had in dates. The fact that that happened tells us that something's wrong with the way that we allocated memory. Can anyone spot what the problem is with how we malloced down here? Yeah, Marble.
Did you account for the size of the data?
Good question. So, does anyone have the documentation for malloc handy? If you just Google malloc, you should see what the argument to malloc is. What's the argument that malloc takes if someone's pulled that up?
Size of type size underscore t.
Okay, yeah, it's so it takes a size t is that, and that size t is in bytes. And right here we've allocated count, and count is the number of elements. And just to show that won't work, we notice that what we're allocating is date t. So a date t is a type that I've defined up here that has a year and a month in it. Both of those are integers. Both of them are likely 32 bits, and there's no way that this whole thing takes up a byte. So the problem here is that when we malloc count down here, we forgot to multiply by the size. So it would be proper for us to do size of followed by date t. And that will allocate many more bytes than what happened previously. Also down here, where we call memset, memset is similar to malloc in that it also takes a number of bytes. So we should also change memset down here to be count times size of date t. And it is the reason why this was causing the crash clear to everyone, because this is kind of, the causation is not immediately clear sometimes. Yeah. What happened, does anyone want to explain it for the people who might not know? Yeah.
So I'm just taking a guess. Since you didn't multiply by the size, you didn't allocate enough memory. So it probably just went outside of the array because it was too small.
Yeah, that's very, very close. It sounds like you got the right idea. What's happening is, just like Marbled said, we didn't allocate enough memory. And so the specific problem we're having here is that we've put data outside of the range of the memory that were allocated. And so then we may not notice the problem immediately, but next time that malloc comes around, it's going to repurpose that memory that we've been using. So basically we've been using an array that has 6 elements in it, and we only malloced like a small fraction of that space. I don't even think it was half. And as soon as malloc gets called later on by some other function, in this case it's actually, if you look at the stack, it's actually printf. Next time printf calls malloc, malloc is going to go over and trash that same memory that we were using, because as far as malloc knows, we're not using that memory. So that's the cause of the problem, because that corrupted our month, and then the month caused the out of bounds array access. So that's kind of a long chain of causality that it can make these type of bugs hard to track down. But let's see if everything is fixed after we made that change. Has everyone multiplied by the size of? Now let's type make in Gdb. This is one handy thing about Gdb, is that you can make while you're still in there, so you don't have to exit. You can keep your watch points and everything. In this case, we don't really want the watch point, so I'm going to type Untitled Breakpoints, and let's see. Oh wait. Okay, there's no watch points. So what I'm going to do now is run from the beginning again, and we can see if our output makes sense. So let's run testcase.txt, run from the beginning. And as you can see, there's no more segfault. So that's great news. Can someone inspect the values and make sure that they make sense though? Specifically, it might help you compare to the correct output, since we have that right here. So, April of 1715, correct. January 1800, correct. February 1900, not correct. It should be 28 days, but it's giving us 29 days. So it's, for some reason, it thinks that that's a leap year, even though it's not. And it seems like we already fixed the problem with detecting leap years. So let's see if we can go in here and figure out what's going on this time. So let's open up daycount.c. And let's run through the basic process that we use to determine how many days are in a given month. So the function that we're calling to get the number of days is just get n days. As we can see here, we begin by getting whether or not this year is a leap year. Then, if the month is not February, then we get the corresponding number of days in the month from our table that's up at the top. Otherwise, we check if leap is true, and we assign either the number of leap days or the number of non-leap days to the number of days, since we know it's February. So in this case, we'd like to probably set a breakpoint and get n days to see what's going on in this function. However, we're going to be calling this function a lot of times, and we probably don't want to hit the breakpoint every single time this function is called. So that's where conditional breakpoints come in handy. What a conditional breakpoint is, it works just like a normal breakpoint, except you can append a conditional statement after the breakpoint statement. And so what this will do is it will break only if x is 5, or if a function of a variable is equal to a value. Once again, it can take arbitrary expressions. So right here, we'll probably want to break only if the year is, 1900. So let's do b line 40 if year equals 1900. Okay. And now we'll run from the beginning again. And then, as you can see, we've hit that breakpoint, and we didn't hit it the first few times. We only hit it when year was 1900 and month was 2 right here. So let's go step by step through this and see what's working and what's not. So first of all, we're calling the isLeapYear function. So let's type n to go to the next line, and now let's type pleap to see if we got a leap year. And as you can see, leap is 0. So that means that our isLeapYear function is doing its job. And in this case, that's not the source of our error. So let's keep going. N leap days, n days, and let's print n days. And n days is 29, even though we just barely saw that it's not a leap year. So obviously something is going wrong with the line that we just barely executed. And can anyone tell just by looking at that what the problem is? Yeah. Exactly. Yeah, great. Does everyone see down here that in this statement we have leap equals true, just a single equal sign? When what we should be doing is we should be evaluating if leap is equal to true. So this is really similar to the famous exploit that was used to give root access on Linux, when it was supposed to be a comparison between the current user ID and root. What it actually did is it assigned root to the current user ID. So the double versus single equals can be a really pervasive bug if you're not really careful, even in professional and very large projects. So let's all change that to be a double equal sign to check if it's true. And now we'll make again in Gdb. And let's delete our breakpoint because we know it's going to work. And we'll run from the beginning. Also note that when I typed run without typing the rest of the statement, like typing in the input file. And in Gdb, you can do this. You can just type run and nothing else, because it will automatically use the last arguments that you used. So I'll type y. And then as we can see here, it's correctly given us the number of days is 28 for February 1900, and everything else looks to be good. So it seems like everything is good at this point. There's just one more check that we'll probably want to do, and this is where Valgrind comes into play. What Valgrind does is actually pronounced Valgrind, if you're being pedantic. It's the name of some like Norse eagle that like guards the gates to Valhalla or something. It's pretty metal. But the idea behind Valgrind is that you can run programs in Valgrind and it will check for all sorts of memory errors. Ordinarily, it's really hard to tell if you have a memory leak in your program because it won't manifest as a bug unless you run out of memory. And so it's always good to use Valgrind to make sure that you're freeing everything that you allocate. And what we're going to do right now is we're going to run our day count program in Valgrind. So if you have Valgrind installed, and you probably do, then just type valgrind./daycount. Test dates. Okay, so what we have here is, if we scroll up a little bit, we see the standard program output right here, just like we normally see. And down here, Valgrind has provided us with a summary of the state of the heap and any leaks that's detected. So from looking at this, do you think there are any problems with our program? I'm seeing a nod. Yeah. What's the problem?
We definitely lost 48 bytes in one block.
Yeah, exactly. So we've got a definite memory leak. And most people here probably know what causes a memory leak, but for those who don't, a memory leak is any time that your program allocates memory that you don't free. So you're taking memory from the heap, but you're never returning it like you should. And so what we're going to do here is we're going to check and make sure that every time we malloc, we're also freeing. So I'm going to blow this up. And here we have our malloc here. And do we have any free? Do we ever free that memory? Nope. So we load dates right here. The load dates function is going to allocate all that memory, and then we return it and we print out information from that memory, and we never free it. So in order to fix that, we're going to add a free statement. And do you think we should do it before or after this for loop here? After. Wow. Great answer. Why should we do it after? Yeah, exactly. We have to access that memory before, and we've already seen what happens when we access memory that's not allocated. So we're going to add a free statement after that, free da.dates. And now we're going to go back and over here, make again, and we can run Valgrind once again. And this time, as we see, no leaks are possible, all of our blocks were freed. So this is the most basic use case of Valgrind. I'm not going to cover the other stuff because this is all you need, like 99% of the time. So that's all that I have prepared today. Are there any specific questions about GDB or Valgrind that you guys had? Okay. If no one has any questions, then that should be that. And I'll stick around a little while after if anyone has any specific examples they want. Thanks.